Alright, in this video we're looking at section 4.1, scatter diagrams and correlation. So here are the objectives for us. We're going to draw and interpret some scatter diagrams, describe properties of linear correlation coefficient, then we'll compute and interpret what that linear coefficient means, determine if a linear relation exists between two variables, and look at the difference between correlation and causation, which are not the same thing, but sometimes can be confused. So first, when we are looking at scatter diagrams, correlation, we need to define a couple of terms here. So the response variable, so when we're looking at correlation, we're going to be looking at a couple of different variables and how they're related to one another. So we have a response variable is the variable whose value can be explained by the explanatory variable or a predictor variable. Okay, so the response variable is just, it's explained by that explanatory variable. And then scatter diagram, this hopefully is not anything new. You've probably seen these before. It's just a graph that shows the relationship between two quantities measured on the same individual. Okay, each individual in the data set is represented by a point on this scatter diagram. And the explanatory variable is on the horizontal axis, and the response variable is on the vertical axis. Okay, you can kind of think of those as independent versus dependent. Again, but the explanatory variable explains the value of the response variable. Okay, so when we look at scatter diagrams, they show us the relationship that exists between two variables, and that's all it is just a relation. It's not necessarily causation. So please don't get those two overlapped and confused. So our goal in interpreting the scatter diagram is just to distinguish diagrams that imply a linear relationship, a nonlinear relationship, or no linear relationship. So when we say linear, okay, embedded in linear is the word line. So they're going to follow a line or a trend. So for example, this graph right here, you can kind of draw a line that that shows the tendency for these variables. As the explanatory variable increases, the response variable increases. And then this one right here is kind of the opposite. As the explanatory variable increases, the response variable decreases. And that's kind of a look at linear. Now you could have something that's nonlinear, so you have this thing that's more parabolic, or you could have something that's nonlinear that's cubic, but they're not linear, but they could definitely look like they're following some kind of trend or pattern that we could model. And then you have no relation, where they're just kind of scattered all over. There's no rhyme or reason to what's going on. Okay. Now, if two variables are linearly related, then they are positively associated when above average values of one variable are associated with above average values of another variable, or vice versa. Below average values of one variable are associated with below average values of another variable. So in other words, if you draw the trend line, if you think of that line that you're drawing, would have a positive slope. So the greater the explanatory variable, the greater the response variable. The lower the explanatory, the lower the response. Okay. Then we have negatively associated, and that's the opposite. So when we have above average for values for one variable, those are associated with below average for the other variable. So basically, as one increases, the other decreases, or vice versa. Okay. But again, if you look at the trend or the slope of those, okay, that's going to be trending downward. So you can think of a negative slope, so they're negatively associated. just remember, positive means they're going the same direction. As one increases, the other increases, or as one gets smaller, the other variable gets smaller. Negative just means they're opposites. As one increases, the other decreases. As one decreases, the other increases. Okay, so here are some questions here. We want to determine whether the scatter diagrams they have a linear relationship if it exists, and if it does exist, determine whether it's a positive or a negative. So our first one looks like we're following this kind of pattern right here, and so we would call this nonlinear because this is actually more exponential than anything. The second one definitely have this downward trend. So again, as the explanatory variable increases, the response variable is decreasing. So that's going to be negative. So it'll be linear and negatively associated. Okay, and then the last one, there's no rhyme or reason to really anything going on there, so we just call it nonlinear. No relation on that. Okay, but it really is as simple as that, just to identify when you're looking at a graph, when you have the scatter diagram. Okay. Now, when we have something that is linear, there is this idea called a linear correlation coefficient, or the Pearson product moment correlation coefficient. We're going to call it the correlation coefficient, is what you'll hear me say. And what that is a measure of the strength and direction of the linear relationship between two quantitative variables. So we will be using the Greek letter rho. That represents the population correlation coefficient, and then lowercase r represents the sample correlation. In almost everything we do, it'll be lowercase r because we'll be dealing with samples. But just know, again, population is rho. It's a Greek letter, which follows kind of the pattern we've been going through with mu and sigma. R is the sample correlation coefficient. So I'm going to present the formula to you for the sample correlation coefficient, but we are not going to be calculating these things out by hand. These are very laborious, and computers are really good at calculating these very quickly, as long as your data is input correctly. Okay, so I'll kind of let you take a big old look at that guy right there as to what it's all talking about. More often used is this formula down here, which is equivalent. Okay, the sum of the x sub I times y sub I minus the sum of x sub I times the sum of y sub I over n divided by the sum of x sub I squared, blah, blah, blah. It's just big. It's nasty. And so if you were to try and do this by hand, here is everything you would do. You would compute x bar. You'd compute the standard deviation of one variable, then y bar and its standard deviation for y. Then you would determine x sub I minus x bar over s sub x, and y sub I minus y bar over s sub y for each and every observation. Determine the sum and substitute. If you were using Formula 1, you'd substitute into Formula 1, and you'd get this big old grizzly thing. Again, we are going to be using technology to find it, but just so you know, kind of where it's coming from, how it's found, but that is beyond the scope of what we're trying to do in this class. Again, we've got technology. Technology is a spectacular tool for us, so we'll go ahead and rely on that for this class. But here are some of the properties of this linear correlation coefficient that are extremely helpful. These you'll definitely want to know. Okay, the linear coefficient is always between -1 and 1 inclusive. So it can be -1, it can be 1, and anything in between. So there's your correlation. So if you get a correlation coefficient, someone says it's -2, not so much. It's not going to work. Okay, if the correlation coefficient is +1, then you have a perfect positive linear relationship that exists between the two variables. If it's -1, you have a perfect negative linear relationship that exists between the two variables. but that's not super likely. But the closer that R is to positive 1, the stronger the evidence of the positive association between the two variables. Similarly, the closer it is to negative 1, the stronger the evidence for a negative association between the two variables. If R gets close to 0, then there's little to no evidence exists of a linear relationship between the two. Although R close to 0 does not imply no relationship. It's just implying no linear relationship. So something with a correlation coefficient, and this is a common misconception, if it's got a correlation coefficient of, say, negative 0.5, that's stronger correlation than 0.3. Some people think that the larger the positive value, the better or more correlation exists. But it's actually the further away you get from 0. So the closer to 0, we have little or no evidence, but the further away, the stronger the evidence, whether we're going in the positive or the negative direction. Okay, the correlation coefficient is a unitless measure. So the units of measure of our variables x and y, they play no role in the actual interpretation of that correlation coefficient R. Okay, the correlation coefficient is not resistant. So if an observation that doesn't follow that overall pattern, the data, it could affect the value of your correlation coefficient quite significantly. So here are some examples of your perfectly positive correlation or linear correlation, perfectly negative, and then you can have strong if they're kind of bunched up, moderate if they still look like they're pulling a trend, but they're kind of jumping all around, and then we have the same thing going in the negative direction down here and here. But then if you just got this scattered mess, that's not going to be a linear correlation, so that's going to be pretty close to 0. And then even this that looks parabolic, like a quadratic, still it's not a linear correlation, or excuse me, a linear relation. So that correlation coefficient is going to be very close to 0. So when they start to trend in a straight line, that's when we're looking at linear stuff. Okay. So we're going to look at this problem number 29. I'll pick it up in the next video since we're running out of time. But that's just a look at our definitions, the setup. Now we're good to go. We're good to take a look at some questions regarding correlation, create some scatter plots, scatter diagrams, and then make some decisions on some questions we'll be asked.